Bismillah ar-Rahman ar-Rahim. Today we'll talk about tangents and concavity to parametric curves. And the situation is the following. We have a parametric curve, which is a curve described by the parametric equations x equals f of t, y equals g of t, t in some interval. And we have arbitrary point xy in the curve, and we have the tangent at this point. Our objective is to find the equation of the tangent, and for that, of course, we need the slope. We'll see now how to compute the slope to the parametric curve. Of course, we make some assumptions. The first assumption will assume that the curve can be represented in the rectangular form y equals kx, usually theoretically. And the second assumption will assume that f, g, and k are differentiable functions in their domains. So how to compute the derivative? How to compute, the slope? The slope can be computed like Math 101. The slope to the tangent is still dy dx. This is the slope. How to compute it if the curve is described by parametric equations? The procedure is to take the connecting equations. We are assuming that the curve can be represented in this form. So now we'll work with this equation. So we have y equals kx. This is the kx. And this implies, now I will just replace x and y by their corresponding parametric equations. So x equals f of t and y equals g of t. Here I have g of t equals k of f of t. Then I will differentiate using the chain rule. So this is g prime of t equals, by the chain rule, it is k prime of f of t times the derivative of the inner f prime of t. So this is really using the chain rule. Now replace there. Replace the values of g prime, k prime, and f prime. So g prime is just dy dt. So this is dy dt. This is k prime. F of t is just x. So this is x. And f prime t is dx dt. Further, I have here dy dt. What is k prime x? If y equals kx, then k prime is just dy dx. Times dx dt. I want to find the derivative dy dx, which will be the slope. So now just solve for dy dx. This is equals dy dt over dx dt. Provided that dx dt not equal to 0. This is how to compute the derivative dy dx of the parametric equations. At a certain value t, we can substitute to get the slope. So this is for the tangents. Now for concavity. For concavity, as in Math 101, you have to find the second derivative. We need to find the second derivative. And we can find the second derivative in almost a similar way. So here, the second derivative for concavity, I need the second derivative, d2 y dx2. Well, I can derive a formula for the second derivative using the formula for the first derivative. How? I can write this in this manner. The first derivative with respect to x of y prime. What is y prime? It is just the first derivative, dy dx, which was already computed in this formula. Now I have dy prime dx. To evaluate the first derivative, apply this formula. This equals dy prime dt over dx dt. Again, provided dx dt not equal to 0. So this is how to compute the second derivative. In fact, we can continue and find higher derivatives, third derivatives, fourth derivative, and etc. in exactly the same way. And just as an example, third derivative of y dx cubed. Write it as a first derivative. It is the first derivative with respect to x of y double prime. What is y double prime? It is the second derivative, which was computed in the previous step. Now apply the formula for the first derivative. This gives us the following: dy double prime dt over dx dt. Again, dx dt has to be different from 0. And so on, and so on. We can continue finding higher derivatives. Now we consider one example. Consider the parametric curve given by the parametric equations x equals t cubed plus 1, y equals t squared minus 3t, t between minus infinity to infinity. The first part, find the equation of the tangent line to the curve at the point corresponding to t equals 1. We need to find the equation of the tangent line, so the solution, as in Math 101, to find the equation of a line, you need a point and a slope. For the point, you have t equals 1, so I have to find the corresponding x and y. When you substitute, you get x equals 2 and y equals minus 2. So the point is just xy equals 2 and minus 2. This is the point. Now for the slope, we need to find the derivative. So first, dy dx. Using the formula, it is dy dt over dx dt. And when you compute dy dt, it is 2t minus 3. Dx dt is 3t squared. So now the slope equals the derivative dy dx at t, or when t equals 1. You substitute 2 minus 3 over 3, and this gives us minus 1 over 3. A point and the slope equation, the equation of that equals y minus 2 plus 2 equals minus 1/3 x minus 2. And this, we can simplify this further and get y equals minus 1/3 x plus 2 over 3 minus plus 2 over 3 minus 2, and hence we get y equals minus 1/3 x minus 4 over 3, minus 4 over 3. The second part of the question is the following. Describe the concavity of the curve. So here we need to compute first the second derivative. From part A, we have the first derivative, dy dx. If you simplify it, this will be 2 over 3 t squared, 2 over 3 t squared, minus 1 over t, squared. So this is y prime. For the second derivative, by the formula, this is again dy prime dx, and this is dy prime dt over dx dt. To compute dy prime dt, this is y prime, so just compute the derivative. This becomes minus 2 over 3 t squared and plus 2 over t cubed over dx dt. So the original equation x 3t squared 3t squared. Simplify a little bit, this becomes a 3t squared, common denominator 3t cubed, and this is minus 2t plus 6. When you simplify, we get minus 2t plus 6 over 9 t power 5. As in Math 101, we have to decide, or we have to check the sign of the second derivative. To find the sign of this, I have to find the zeros of the numerator and denominator. So zeros, from the numerators, I have t equals 3 minus 2t plus 6 equal to 0. This gives me t equals 3. The denominator, 9t power 5 equal to 0. This gives us t equal to 0. So these are the zeros of the numerator and denominator. Now in the number line, I have the zeros 0 and 3. I have to check the sign of the second derivative. And for that, we need only take test values in each interval. Okay? Here, if I take minus 2, this becomes negative, the sign. You substitute, you get a negative. Take at its value 1, substitute here, you get positive, the sign is positive. Take 10, for example, here, this is positive and this is negative. Okay? So this means concave, this is concave down, this is concave up, this is concave down. So the conclusion is the following: the curve is concave up, when t is between 0 and 3, concave down, when t between minus infinity and 0, and t between 3 and infinity. That's it. We consider the first example here. Find an equation for the tangent line to the parametric curve given by the parametric equations at the point corresponding to t equal to 0. For the solution, it is just finding an equation of a line, and for a line, to find the equation of a line, we need a point and the slope. For the point, when t equal to 0, I have to find the corresponding point. So I have to find what is x and what is y. Substitute. When t equal to 0, you get 0 plus e power 0, 1. And when y equal to 0, you get 3 minus 1, which is 2. So the corresponding point is 1 and 2. This is for the point. For the slope, I have to find dy dx first. So what is dy dx? dy dx. We have a formula for the derivative, which is dy dt over dx dt. Of course, provided the denominator is not equal to 0. Now differentiate for y, the derivative with respect to t, this becomes minus e power t. For the denominator, derivative of x, this becomes 1 plus 2 e power 2t. This is the derivative, dy dx. For the slope, it is the derivative, dy dx, at the value t equal to 0. At the value t equal to 0. Substitute, you get the following: minus e power 0, 1 plus 2 e power 0, and this is just minus 1 over 3. A point and slope, or from 0, 0, 1, equation of the tangent is the following: a y minus the 2 equals the slope minus 1/3, x minus 1. We can simplify further to get y equals minus 1/3 x plus 1/3 plus 2. And hence we get the following: y equals minus 1/3 x plus 7 over 3. This is the equation of the required tangent line. We consider the following example. Find the points on the parametric curve given by the given parametric equations at which the tangent line is horizontal or vertical. The problem is about tangent lines and situations at which the tangent is horizontal or vertical. For the tangent line to be horizontal, well, the slope has to be 0. And for the tangent line to be vertical, the slope has to be undefined. The problem or the answer depends on the computation of the slope. How to find the slope? We have to find the derivative. So this is the derivative, dy dx, and it is given by dy dt over dt over dx dt. This is the general formula for the derivative. Now for the horizontal, for the tangent to be horizontal, we have to have the slope, which is the dy dx, at the corresponding value of t. The value of this derivative is 0. From the formula, this is possible only if the numerator equal to 0 and the denominator is not equal to 0. You have to find dy dt has to be equal to 0 and the denominator dx dt not equal to 0. So we have to find the values of t that satisfy these two conditions. For that, we have to compute dy dt and dx dt. So what is dy dt here? Dy dt. The derivative of y, 3t squared minus 12. Find the zeros. So this is just when you factor, this is 3t squared minus 4. Factor further, you get t minus 2, t plus 2. If it is 0, if the dy dt equal to 0, then I get t equals minus 2 and t equals 2. So these are the points of t at which the dy dt equal to 0. Find also the zeros of the denominator, which is dx dt. Dx dt. Find the derivative, it is 2t. What is the zeros? I have only one 0, so this is t equal to 0. So these are the zeros of dy dt and the zeros of dx dt. I want the values of t. That will be a 0 for the dy dt and it is not 0 for dx dt. And it is obvious that really the zeros of dy dt, they are minus 2 and 2. They will make dy dt equal to 0. They also will not make dx dt equal to 0 because the dx dt is 0 when t equal to 0. So if t is different from 0, dx dt will be different from 0 also. So the required values, so this gives us the two values, t equals minus 2 and t equals 2. At these values, these two conditions are satisfied. Find the corresponding points x and y. When t equals minus 2, I get x equals 4 and y minus 8 plus 24, it is 16. And when t equals 2, I get also 4 and 8 minus 24 minus 16. So at these 2 points on the parametric curve, the tangent line will be horizontal. For the vertical tangent, well, I have to have dy dt not equal to 0 and dx dt to be 0. So that in the limit you will get the derivative, the value of the derivative will be plus or minus infinity. So here I have to check, I have to have dy dt not equal to 0 and dx dt equal to 0. Again, I have to know what are the zeros of dy dt and the zeros of dx dt. And they are already calculated. The zeros of dy dt are minus 2 and 2. The zeros of dx dt are, there is only one, which is only 0. So the value of t that will satisfy the second condition is just t equal to 0. T equal to 0. And t equal to 0 is not also a 0 for dy dt. So it also satisfies the first condition. So here I get only one value of t, which is t equal to 0. The value t equal to 0 will satisfy these two conditions. Okay. What is the corresponding point? Well, x and y. When t equal to 0, I get 0, and y will be again 0. So at the origin, at the point 0, 0, the tangent line will be vertical. The tangent line will be vertical. We consider example 3, which states the following. Find for the parametric curve given by these parametric equations, find the second derivative of y with respect to x. Second derivative. To find the second derivative, we have first to find the first derivative. So the first derivative, we have a formula for it. So this is dy dx. The formula is given as follows: dy dt over dx dt. So we have to differentiate y and x with respect to t. For the numerator, differentiate y with respect to t and use the chain rule. Derivative of sine cube, this becomes 3 sine squared t times derivative of sine, which is cosine t, over the derivative of x, which is derivative of cosine cube, this is 3 cosine squared t, times derivative of cosine, which is minus sine t. Simplify. 3 with the 3 will cancel. I have only just one negative sign, so this is minus. One sine with one sine, I get sine t, and one cosine with one cosine, I get cosine t. So this is minus tan t. This is the first derivative, and I will call it y prime, another notation. This is y prime. For the second derivative, well, I have the following: d2y dx. We write this in terms of a first derivative. This is the first derivative of the first derivative, which is y prime, d dx. It is the first derivative of y prime. Now I apply the formula dy prime dt over dx dt. Now what is y prime? Y prime is just the first derivative. which was already calculated. So the derivative of this becomes minus secant squared t. This is the derivative of y prime. Derivative of x, well, it is just 3 cosine squared t times minus sine t. You can simplify here. Notice negative sign with negative sign will cancel. Cosine squared, when you bring it in the numerator, it becomes secant squared. Secant squared and secant squared, which is secant power 4 t. 1 over sine minus cosecant. This is just cosecant. This is the second derivative. We consider now example 4. Study the concavity of the parametric curve. For the concavity, we have to find the second derivative and study the sign of the second derivative. And for that, we have first to find the first derivative. So this is dy dx, and this equals by the formula dy dt over dx dt. And just compute the derivative of y. For y, I have to use the product rule. So this is t e power minus t times minus plus e minus t times 1. This is by the product rule. Over the derivative of x, which is 0 plus e power t. Simplify this because I need to find the second derivative. So it is better to simplify this. We'll just bring e power t up. This becomes e power minus t times minus t e power minus t plus e minus t. Again, take e power minus t as a common factor. This becomes e power minus 2t minus t plus 1. E minus t with e minus t, you get e minus e power minus 2. This is the first derivative, and let me call it just y prime. For the second derivative of y with respect to x, it is the first derivative of y prime. Derivative of the derivative of the first derivative with respect to x. Again, the formula dy prime dt over dx dt. How to find dy prime dt? Well, this is y prime. So just differentiate it with respect to t. Again, use the chain rule, the product rule. The first, e minus 2t, times derivative of the second, minus 1, plus the second, minus t plus 1, times derivative of the first, minus 2e minus 2t. Over the derivative of x, which is e power t. Next, we have just to simplify it. So from the numerator, I have e minus 2t, a common factor. I get minus 1 plus minus t plus 1 times minus 2 over e power t. Again, bring e power t up. It becomes e power minus t. So this becomes e power minus 3t. And here, just multiply and simplify. This is 2t. Minus 2 minus 1 minus 3. This is the second derivative. Now for concavity, I have to check the sign of the second derivative. And to check the sign of the second derivative, find the zeros. So what are the zeros of the second derivative? Let this e minus 3t, 2t minus 3 equal to 0. This gives us 2t minus 3 equal to 0, because the exponential function e power minus 3t is never 0, so I can divide by it. When you divide by it, you get 2t minus 3 equal to 0, and the solution will be t equals 3 over 2. So there is 1 0 for the second derivative. To check the sign, just draw the number line. I have the 0, t 3 over 2. What is the sign? Sign of the second derivative, which is this one. For that, you just choose test values. So here, if I take, for example, here a number greater than 3 over 2, for example, 2, I get 4 minus 3, 1, positive, e power minus 6, positive. So the sign of the second derivative here is positive. If I take a value here less than 3 over 2, for example, 0, substitute 0 minus 3, negative, times 1, negative. So this is negative. This means the curve is concave down on the interval minus infinity to 3 over 2. Minus infinity to 3 over 2. And concave up on the remaining interval, 3 over 2 to infinity. So when t is between minus infinity to 3 over 2, the curve is concave down, and when t is between 3 over 2 and infinity, the curve is concave up. This is the concavity of the given curve. Bismillah ar-Rahman ar-Rahim. In this video, we'll talk about areas with parametric curves, and we'll restrict ourselves to regions bounded by the parametric curve and the x-axis or the y-axis. We'll see really the situation is similar to the situation of Math 102, computing areas with in rectangular forms. And for that, let's start with Math 102. So one basic case in Math 102 is to compute the area of this region bounded between the x-axis over the interval AB and the curve given by y equals h of x, under the assumption that really h of x is positive on the interval AB. In Math 102, the area of this region is computed as follows. The area equals integral of the function h of x dx over the interval a to b. We can write this also as just integral from a to b. H of x, the function, the name of the function is y, so I can write y dx. This is what we do in Math 102. Now in parametric forms, if the same curve is parameterized by the following parametric equations: x equals f of t, y equals g of t, over the interval of t from alpha to b. Here we have to make one assumption. Basically, the curve is traced once in the interval alpha to beta. Under this assumption, how to compute the area of this region? In fact, just like Math 102, we have to use the same formula, but in parametric form, i.e. just make a substitution, replace y and dx from the parametric equations. So we will get the following. The area here in parametric form, area equals the integral. You start from a to b in the rectangular form, y dx. We make a substitution. Just substitute y and dx from their corresponding parametric equations. So this becomes the following. Integral y is just g of t, and dx equals f prime t, f prime, the differential f prime of t dt. Now we have to change the limit. The limit in rectangular forms goes from x equals a to x equals b. Now what are the corresponding limits for t? Now here, just like Math 101, now if x equals a, what is the corresponding t? If x equals b, what is the corresponding t? use the given equation relating x and t. Here you have x equals f of t. So if x equals a, you get a equals f of t, and then you solve for t, and you will get either alpha or beta. Let's say, for example, alpha here, and then x equals beta or beta. If x equals b, find the corresponding t by solving, and then you get t equals beta or alpha. In this case, we get alpha to beta or beta to alpha. G of t f prime of t d dt. We get this variation because, remember, when you describe parametric curves, we have the direction is important. Okay? So this follows from really the directions. Okay? This is the formula. This is the formula for the area. Always we have to check that also y positive. So here, just make sure that really y is positive. Y is positive on the corresponding now on the interval alpha to beta. We have to make sure that y is positive. That's it. In a similar way, if the region is on the y-axis, so again, like Math 102, you have this basic region between the interval CD on the y-axis and the curve x equal w of y, under the assumption that y is positive on the interval CD. From Math 102, the area is just the integral of w of y dy from c to d, which is just x dy. If the curve, the same curve, is described by parametric equations, then the formula is the same. You take the same formula and then you substitute the values of x and dy. X equals f of t, dy equals g prime t dt, and then you have to change y equals c, what is the corresponding t, and when y equals d, what is the corresponding t, using this equation. You will get either from alpha to beta or beta to alpha. So the two situations are similar. Let's now illustrate this with one example. Let's consider this example. Find the area of the region between the x-axis and the parametric curve x equals t squared, y equals t power 4 plus 1 over the interval from 0 to 2. Now to solve this, the region is above the x-axis. So the formula from the first case, the area will be given in this manner. Integral from a to b y dx. This is the rectangular form. So here we have the interval t between 0 and 2. In fact, we can find a and b. Since x equals t squared, so we have 0 less than t squared less than 4, and hence 0 less than x less than 4. So the x interval is from 0 to 4. Of course, to apply this formula is applicable under the assumption that y is positive on the given interval. So I have to check that y is positive on this interval. It is very obvious that y equals really t power 4 plus 1. T power 4 is always positive, plus 1 is always positive, so really we have greater than or equal to 0 for all t, and especially for the interval of t between 0 and 2. 0. So y is positive, so this formula is correct. Now we have just to substitute the value of y and substitute the value of x dx with the corresponding elements. So a equals integral y dx from 0 to 4, and this equals y is t power 4 plus 1, dx is 2t dt, and the t interval will go from 0 to 2. If x equal to 0, I get t equal to 0. If x equals 4, I get x equals 2. Now we just integrate, so this we can take the 2 outside. You get 0 to 2 t power 5 plus t dt, and then this 2 t power 6 over 6 plus t power 2 over 2 from 0 to 2. You substitute, we get the answer is 76 over 3. Let's now consider the following example. Find the area of the region lying in the first quadrant and enclosed by the x-axis and the parametric curve x equals t cubed plus 1 and y equals 2t minus t squared. It is an area problem, so initially, since the region is is above the x-axis, so the formula is directly the following: a equals integral from a to b y dx. This is the initial formula for the area. But notice here in the question, there is no time interval given. The interval is not given, so we have to find the time interval. Well, how to find it? Remember that when we use this formula, we are making the assumption that y is positive. So really, to find the t interval, we have to ask when is y positive. So, or in which t interval is y positive. So here, when is y positive? Okay. To decide this, let's take the equation for y, and see when it is positive. So here y equals 2t minus t squared. If you want to check the sign, I have to find the zeros. Make this equal to 0. This gives us t, 2 minus t equal to 0. And hence we have the following. We have this t equal to 0 and t equals 2. To check the sign of y, now just use the number line. This is 0, t equal to 0, and this is t equals 2. And check the sign of y, which is y equals 2t minus t squared. To check the sign, I have to take a test value in each interval and substitute and find the sign. So if I take t equals 1, I get here positive. If I take t equals minus 1, I get negative. If I take t equals 3, I get negative. So now I notice that really here y is positive. So y is positive when t between 0 and 2. Notice this will give us then I can find the corresponding x values. If x equals t cubed plus 1, then just cube each side and then add 1. This gives us t cubed plus 1 less than 9 and greater than 1, i.e. x is between 1 and 9. Notice that really x is increasing. Okay, so this gives us the area equals, in the same formula here, y dx, y 2t minus t squared, 2t minus t squared, times dx, which is 3t squared, dt, and the time interval from 0 to 2. We just now compute, take the constant 3 outside, 0 to 2. This is 2t cubed minus t power 4 dt, and then integrate. This is 3. This is t power 4 over 4, 2 minus t power 5 over 5 from 0 to 2. And then compute. This is very simple. This is just 3. You have 8 minus 32 over 5. I take 8 as a common factor, we get 24. This is 1 minus 4 over 5. And this is just 24 over 5. Let's consider this problem. Find the area enclosed by the ellipse given by the parametric equations x equals cosine t, y equal to sine t over the time interval from 0 to 2 pi. Here to start the solution, it will be nice just to sketch the ellipse really. But change this to Cartesian equation using the basic trig identity, which is cosine squared t plus sine squared t equals 1. This gives us x squared plus and sine t y over 2 squared y squared over 4 equals 1. This is the equation of an ellipse, and we can sketch it. This is the sketch. This is the graph of this ellipse. This is 2 minus 2, 1 and minus 1. We can also check the direction. When we take t equal to 0, I get this point 1 and 0. So this is t equal to 0. When t equals pi over 2, I am here, t pi over 2. T equals pi, I am here, t equals pi. So really the direction is counterclockwise. And when you continue, this is t equals pi, and this is t equals 2 pi. This is the ellipse, and this is the region here. Now to find the area of this region, by symmetry, I will just concentrate on the upper part, the part above the x-axis. So it is enough to find the area of this region and then multiply by 2. So this region here, t, between 0 and pi. Notice in the parametric forms, through this direction, x is decreasing. Now, a rectangular form, well, the area is what? Area equals the area of this part is just integral from minus 1 to 1 y dx. This is the area of the upper part. But I need the area of the whole part, okay? Everything inside the ellipse, so I have to multiply by 2. So this is h2. This is the formula in rectangular form. Now go to parametric form. Now replace y by its value and find the x of the given x. So this gives us the following: 2 integral y is just 2 sine t, dx is minus sine t dt. What about the limits? Now here you just make a change. If x equals minus 1, what is the corresponding t? X equals minus 1. This gives us x is just cosine t. So this cosine t equals minus 1, and hence t equals pi. When x equals 1, I get cosine t equals 1, and the corresponding t equal to 0. We have to find the values of t restricted to the given range from 0 to pi. So this gives us the following: the limits minus 1 becomes pi here, and 1 becomes 0. Simplify. I will take the 2 outside. I get 4. Here, sine squared dt. I have a minus. Well, to get rid of the minus, I have to switch the limits of integration. So this becomes 0 to pi. This is one of the properties of definite integral. So I have now this integral. Just go and compute it using the usual technique. So this is 4, 0 to pi. Sine squared is just 1 minus cosine 2t over 2 dt. Take the 2 outside, this becomes 2, 0 to pi, 1 minus cosine 2t dt. It is very simple to integrate. This becomes 2. This is t minus half sine 2t from 0 to pi. And this is just 2. And this is pi minus 0. And this is 2 pi. So the area equals 2 pi. That's it. Bismillah ar-Rahman ar-Rahim. In this video, we will discuss the problem of arc length and surface area in parametric forms. And for that, we have the following. So let's have the following parametric curve described by the parametric equations x equals f of t, y equals g of t, on the interval t from alpha to beta. Here we make two assumptions. The first assumption, we have to make sure that the curve is traced only once in the interval alpha and beta. And we have to assume that the derivative f prime and g prime are continuous in the interval alpha beta. Under these assumptions, the length of the curve will be given by this formula, integral from alpha to beta, square root of the square of the derivative of x with respect to t plus the square of the derivative of y with respect to t. And for the area of the surface, we have two cases. The area of the surface generated by revolving the curve about the x-axis, and here we have to assume that y is positive, is given by this formula, the integral of 2 pi y square root of the same quantity given in the arc length. If the rotation is about the y-axis, we may have to make sure that x is positive. And the formula is really similar to the first formula, which is the integral of 2 pi x square root of the same quantity with the arc length. Here just a note, just to simplify memorization, when the rotation is about x-axis, in the integral we have y from x to y. And when the rotation is about the y-axis, in the integral we have x. So just replace y with x. The proofs of these formulas are really similar to those given in calculus 2. So I advise you just to check your calculus textbook for the details of the proof. But now we'll illustrate this with some examples. We start with the first example. Find the length of the parametric curve x equals 3t, y equals 2, t power 3 over 2 over the interval from 0 to 3. Here, we need to apply the formula directly. And the formula for the length is given by the following. That is from 0 to 3, the interval, and square root of dx dt squared plus dy dt squared dt. So we have to compute the derivatives and square them and then simplify. Always it is preferable just to make the solution more organized. It is preferable to find the root in the margin. So first find the derivative. So this is dx dt equals 3 and dy dt. When you differentiate, we get 2 times 3 over 2 t power half. This is 3 square root of t. Now take the squares and add them, dx dt square plus dy dt squared. When you square this, you get 9 plus the square of dy dt is 9t. And this is just 9, 1 plus t. Now take the square root of the same quantity, dx dt square plus dy dt. Well, this is root 9, 1 plus t. And this is just 3 root 1 plus t. Now this is quantity, this is the integrand. Now just substitute here, you get the following: 0 to 3. The radical equals 3 root 1 plus t dt. Now integrate the square root, so we take the 3 outside. This is 1 plus t or 3 over 2 times 2 over 3 from 0 to 3. And this is just 2. Substitute, get 4 over 3 over 2 minus when t equal to 0, we get 1. And this is just 2 times 4 square root of 4, 2 power 3, 8 minus 1, and we get 4, 14. So the length of this parametric curve is 14 units. We consider another example. Find the area of the surface generated by revolving the parametric curve x equals t squared, y equals t minus 1/3 t cube over the interval 0 to 1 about the x-axis. Again, the formula, just apply the formula directly. So this is the formula S, integral 2 pi. Now we are rotating about the x-axis. We have to multiply by y, and then the root of dx dt squared plus dy dt squared d dt from 0 to 1. Of course, here we have to check that really y is positive, and it is very simple to see that really y is positive on the interval 0, 1, on the interval 0, 0, 1. Then we have just to substitute, plug in the quantities in the integral and simplify. And as usual, it is better to simplify it. Just work with the root outside and simplify it first. Here, dx dt, just the derivative dx dt equals 2t, and dy dt equals 1 minus t squared. Square and add dx dt square plus dy dt squared. The first, we get 4t squared plus the second one, this is 1 minus 2t squared plus t power 4. When you add them, you get 1 plus 4 minus 2 plus 2 t squared plus t power 4. And we observe that really this polynomial is a perfect sequence. This is just 1 plus t squared all squared. So when you take the square root, of this quantity, you get absolute value 1 plus t squared. But since 1 plus t squared is always positive, so it comes out as 1 plus t squared. Plug in, so now this becomes the following. S equals, take 2 pi outside as a constant, integral from 0 to 1 of y. Y is given by the equation t minus 1/3 t cubed times the square root, which was simplified as 1 plus t squared, 1 plus t squared, and d dt. To integrate this, you just multiply the two polynomials. This equals 2 pi, 0 to 1. When you multiply, you get t cubed minus 1/3 plus 2 over 3 t cubed minus 1/3 t power 5 d dt. A very simple function to integrate. This becomes equals 2 pi half t squared plus 2 over 9 plus 2 over 12 t power 4 minus 1 over 18 minus 1 over 18 t power 6 from 0 to 1, from 0 to 1. A substitute, you get the following. This is just 2 pi. When t equals 1, you get 1 over 2 plus 1 over 6 minus 1 over 18. This is when t equals 1 minus when t equal to 0, you get this 1. So this is the simplify. This is h2 pi. This is just the common denominator is 18, and you have here 9 plus 3 minus 1, and this is 2 pi. This is 18, 12 and 11. Okay, and this is just 11 pi over 9. So the surface area is 11 pi over 9. That's it. Okay. Let's now consider the following example. Find the length of the parametric curve given by these two parametric equations over the interval 0 to pi over 2. Here we just apply the formula directly. So this is integral from 0 to pi over 2 square root of dx dt squared plus dy dt squared dt. To make our solution more organized, we just compute the derivative outside in the margin, simplify, and then plug them back in the integral. If I start with we start with dx dt, x equals e power t sine t. So to find the derivative, we apply the product rule. So it is the first e power t times derivative of the second cosine t plus the second sine t times the derivative of the first, which is e power t. Square this quantity, dx dt. Okay. So when you square this, you get the first square, e power 2t cosine square t plus 2 times the first times the second, e power 2t sine t cosine t plus the second term squared, and this is e power 2t sine squared t. It is better to simplify this long expression, and you notice the following. Really, you have e power 2t as a common factor, so e power 2t. What remains is cosine squared t plus 2 sine t cosine t plus sine squared t. We also can simplify further what is inside the parentheses. You have e power 2t, have cosine square plus sine square, it is 1, so this is just 1 plus. Now again we can combine these three terms, 2 sine cosine, by using a basic trig identity, sine 2t. This is for dx dt. You do the same thing for dy dt. Similarly, dy dt. In fact, I will leave this for you. When you compute the derivative and then square, you will get exactly the same except for a minus sign, e power 2t, 1 minus sine 2t. You can check this. Now you add them, dx dt plus dy dt squared. When you add them, just e power 2t is a common factor, e power 2t is a common factor, and here 1 plus 1, 2, plus 0, and this is just 2 e power 2t. Plug in the formula now, so this equals 0 to pi over 2 square root of 2 e power 2t dt. square root of 2, a constant, so you can take it outside. This is square root of 2, and this is square root of e power 2t dt. And root 2 is a constant outside, 0 to pi over 2. Square root of e power 2t is just e power t dt. You see, after the simplification, the integrand is very simple. So this becomes root 2. The integral e power t from 0 to pi over 2. Substitute, you get the following: root 2 e power pi over 2 minus 1. And this is the arc length of the given curve. Let's consider the following example. Find the area of the surface generated by revolving the parametric curve about the y-axis. Again, we apply the formula directly. The formula is given as follows: integral 2 pi. We are revolving about the y-axis. We have to multiply by x, so this is x. And this is square root of dx dt squared plus dy dt squared dt over the interval from 1 to 4. Also, we have just to make sure that really x is positive on the interval, and clearly x is positive on this on the interval 1 to 4. Okay, on t between 1 and 4. So we can apply the formula directly. Now we just need to simplify, to compute and then simplify. So again, to make our calculation more organized, do the calculation in the margin. I need to find the two derivatives and square them. For x, dx dt equals, we'll apply the derivative rules of math 101. So this is 1 over 2 root 32 t times by the chain rule 32. And this is just 16 over root 32 t. When I square, so this implies dx dt squared, you get 16 squared over 32 t, which can be simplified as 8 over t. 8 over t. This is for dx dt. You do the same thing for dy dt. So dy dt, when you differentiate, we get 2t minus 1 over t squared. Okay, so this implies dy dt squared. This becomes 4t squared minus 4 over t plus 1 over t power over 4. This is the square of dy dt. Now we add them. Dx dt squared plus dy dt squared. This is 8 over t plus the second one, which is 4t squared minus 4 over t plus 1 over t power 4. What is the first and the middle and the third term? You can add them. You get 4t squared. When you add these two terms, you get plus 4 over t plus 1 over t power 4. But really, notice, really this is, these three terms are the same exactly the same as this 3 term, which comes from the square of this one, i.e. this is just a perfect square. So this is just 2t plus 1 over t squared on square. Now take the square root of this quantity. It becomes absolute value of 2t plus 1 over t squared. But our interval for t from 1 to 4 positive values, so everything here will be positive. So we can remove the absolute value, 2t plus 1 over t squared. This is the square root. Now just substitute here, so this equals, take 2 by outside, integral 1 to 4 x, which is root 32 t, times the root, which was simplified here to be 2t plus 1 over t squared dt. Again, simplify the square root of 32t. This becomes 2 by, this is root 32, take it outside, integral 1 to 4 root t, 2t plus 1 over t squared dt. To integrate, first we have to multiply. Okay, this becomes integral from 1 to 4 root 32. This is 16 times 2, 4, هتكون 8 by root 2. When you simplify this, now this is t power half, multiply with 2, t power 3 over 2 plus t power minus 3 over 2 dt. This is when you simplify. Now you integrate using the very simple integral here, 2. This becomes 2 times t power 5 over 2 times 2 over 5 plus t power minus half times minus 2 from 1 to 4. Okay. When you compute, we'll leave the calculation for you. Okay. When you compute, we get 1032 over 15 by root 2 over 5 by root 2. This is the answer. That's it.